Okay. We'll go ahead and get started. Thanks for coming today. More people today. Had 6 this morning. Good. I know there's lots of things to do on a Friday during COVID-19, so thank you for being here. For Thermo. Okay. Today we're going to talk about the lecture that was given on Wednesday, and it involves work and modes of work that we have to deal with. And so I want to review those modes of work first for the first 5 minutes, and then I have some problems for you to look into. So first of all, we have, if we have volume doesn't change. This is when the word that we're going to see in our problems is going to be rigid container. That's going to be easy for us. Wherever we see the rigid container, we know that work, the boundary work, is equal to 0. Now, boundary work is because that boundary is changing. Okay, look, I know the nomenclature. The boundary is changing. Boundary work is going to be 0 for that case. Okay. The other type of work we can talk about is constant pressure. Constant pressure work. Okay, and so we know that work is equal to the integral of P dV from state 1 to state 2. That is correct, always correct. We can take pressure, if it's constant, out of the integral, and we get pressure times V2 minus V1, okay? Now, sometimes in some problems, we're not given pressure, not given volume, we're given specific volume. And so we would write this as mass times pressure times specific volume 2 minus specific volume 1. Sorry. So we can always convert between volume and specific volume, always. Okay, don't let that catch you off guard. All right, now, if a problem, let me go on to the next thing, and then I'll get back to this. I was getting ahead of myself. There are other situations for boundary work. This is again boundary work that is polytropic. Polytropic is the one that we talked about, or polytropic, however you want to say that. Polytropic is saying that, you know what, the pressure and the volume, they both change, and we can graph them, and what we're modeling this is we're to put a best fit line through this, and this best fit line is going to be PV to the N is equal to some constant value. Okay, this is going to be a power series that we're going to put something to. So there's an alternative homework assignment that's out that I released this morning where you can explore how to best fit some lines to some points, okay, and show me how that curve looks. Now, polytropic is telling us, like I said, that PV to the N is equal to constant. Students all the time in this class want to make work polytropic all the time. I'm going to tell you very clearly, unless the problem statement says polytropic work, or unless the problem statement says the pressure and volume are related by some N, or unless they say PV to the something, it's not polytropic. If it doesn't tell you, give you some hint that it's polytropic, and hint's probably too weak of a word. It will be very direct that it's polytropic. You're going to assume it's constant pressure. Okay, don't make the problem harder by making it polytropic when it's not. And polytropic isn't hard, but I think constant pressure is much easier. Okay, so if we do that, well, we can say here there are things when N is equal to 1. Okay, so this is going to look as PV is equal to constant. Now, students mess with this all the time. PV is equal to constant. They don't understand. What's the exponent there? It's just to 1. Anything to the 1 power is itself. And whenever you see this, the boundary work is going to be equal to P1 V1 natural log of V2 over V1, or P2 V2 natural log of V2 all over V1. Now note, P1 V1 equals P2 V2 because P times V is equal to constant. So P1V1 equals P2V2 equals P3V3, whatever. Okay, that's the key. That's what's happening here. Okay, now, let's just say we had specific volume. We could write this as mass times P1 specific volume 1 natural log V2 all over V1. Or mass times P2 little v2 natural log of V2 all over V1. We could write it in the specific volume way as well. If n does not equal 0 or 1, everything else, we're going to have PV to the n is equal to constant. Okay, and so that's going to give me that the boundary work is going to equal P2V2 minus P1V1 all over 1 minus n, always, always, always. Or you can write this as mass times P2V2 minus P1V1 all over 1 minus n. Always, always on the equation sheet. Don't have to memorize it. There it is for you. One thing I want to tell you is that when you're looking at these equations, if you're looking at this equation here or this equation here, and I ask you to draw it on a PV diagram, you're going to draw a curved line. Students all the time think, they write to me and they say PV, when I have the n is equal to 1, they say that's a straight line. And I say, no, it's not a straight line. And they say, yes, it is a straight line. And I say, why do you think it's a straight line? Because it's to the first power, to 1. And I don't understand where the connection is that because n is equal to 1, it's a straight line. Okay? Maybe it's because 1 itself is a straight line. I have no idea. But it's a very common problem. Don't do it. You will lose points if I ask you to draw the diagram and you don't draw some curve in that line. It needs to have a curve. I encourage you to get on Excel and graph some things out and see how it looks. Power series. A power function. Not power series. Are there any questions about the lecture that we had? Anything that you want to clarify before I go into some other stuff here? Okay, so what are some things I could do? What are some things I've done in the past? Okay, I could give you a list of pressures and volumes on the exam. I could say, here's pressure 1, volume 1. Here's pressure 2, volume 2. Here's pressure 3, volume 3. Here's pressure 4, volume 4. And I could say, find the work from 1 to 4. Find the total work if you know these pressure and volumes. Well, now, I haven't told you if it's polytropic or I haven't told you if it's constant pressure, but if you look at the pressures and P1 and P2 and P3 and P4 are the same, it's a constant pressure process. If P1 and V1, if they have some sort of, if they're different, there's going to be something polytropic. And so you're going to have to figure out what the exponent is because I haven't told you what the exponent is here. So you're going to set two of these pairs and you're going to say P1 V1 to the n is equal to P2 V2 to the n. And you're going to solve for n because it's the only unknown there. And you're going to have to remember how to use logs. And you're going to have to remember how to use your calculator to use logs. Okay, so I'll just show you here. We're going to go P1 all over P2 is equal to V2 over V1 to the n. That's the first thing we can do using the rules of exponents. And then we can use logs here. Basically, log of P1 all over P2 is equal to n times ln of V2 all over V1. And now it's pretty easy to solve for n. And we know what n is. We can find out what n is. Now, we could use any two pairs to find this. We could use P1V1 and P2V2, or P1V1 and P3V3, or P2V2 and P4V4, any of those two pairs, because we are saying with polytropic that PV to the n is equal to constant. So any of those two pairs should give us a constant. Now, truthfully, in the real world, if I was giving you a real world problem, not a made-up problem that is for thermo, you might find that if you take some of those pairs, that the n value you get for one of the pairs is a little bit different than the n value you get for the other pairs. you might get, if I did this one, P1 and P2, I might have got n is equal to 1.21. And if I use P1 and P3, I might get n is equal to 1.22 or something like that. That's because we're trying to find a best fit line through there. Okay, the best thing to do would be to graph it on Excel and put a best fit line through those. But that's what we could do. That's how we find it's called the polytropic exponent. That's how we find that. If I made up a problem on the exam, it would make sure that whatever you did here, you would get the same polytropic exponent no matter which two pairs you used. That's how I would make it up. Now the other thing, and I've given this problem before on the exam. I can't remember when I gave this problem on the exam. And I asked them, and they found n. They found n. Pretty much everybody got found n, and then they had to find out what is the work for the process. And they went to their equation sheet, and they said, okay, n is not equal to 0 or 1, so they wrote work is equal to P2, B2 minus P1, V1, all over 1 minus n, and they went up here, and they took these two entries, and they put it in there to find the work. And that's not the right answer. Because if you look at this graph, PV, and you look at these points, if you only went between those first two, you would be only finding this area under the curve. That's not what I wanted. I wanted the entire work. So you have to go through all 4 points. Okay? You can find all 4 points. And so just because the equation says P2, point 2 and point 1, what I'm trying to say there is final and initial. Now, some students went through this and they said, okay, I'm going to do between these 2 points and find its work, between these 2 points and find its work, and between these 2 points and find its work. And they found 3 different works, and then they added them up. That's okay. You can do that. It's a lot more work than you need to do, but you can do that. What I was hoping for students to do is that the work is equal to P4 V4 minus P1 V1 all over 1 minus n. I want you to understand how these equations work, where they come from, how you can play with them, and not get stuck into looking at that, well, that equation says 2 and 1. Do I have to use 2 and 1? Because you know, just as well as I know, when you get into a testing environment, no matter how strong you are in it, there's always those seeds of doubt that come in. And sometimes I'm purposely doing things. I give you extra information. I do that kind of thing to see if you know it. Okay? Because the world is full of all sorts of extra information. Never have I ever had a problem in my real life that has given me exactly what I need and the equation I need to plug it in. Never. I wish it was. It's always given me this other data, and I'm thinking, should I use that data or not? Okay, so that's what I'm going to try to help you with. Now, I'm not going to try to it should be obvious that data should be thrown out. But those are kind of things you have to be comfortable with. Okay? How about this? Any questions on this? All righty, let's do a couple problems, and then I'll let you have a Friday. So the problem I'm going to do is sort of like, I've already talked about some things that's sort of like a problem on your homework. The next problem I'm going to do is going to be like what's on your homework as well. And again, my hope is that you come here today and you feel like, okay, I can kind of get ahead on my homework now. You're going to have air in a piston cylinder. Okay, and so here's what we're going to say. It undergoes 3 processes. Process 1 to 2 is compression. And they tell us that the compression says that, and they say PV is equal to constant. So already we know that this is a polytropic compression process from 1 to 2. And they tell me that P1 is equal to 10 psi, and V1 is equal to 4 feet cubed, and they tell me that P2 is equal to 50 psi. That's all they tell me. Okay. The next process, from point 2 to point 3, they tell me it's constant volume. to state 3, where the P3 is equal to 10 psi. And process 3 to 1, they tell me is constant pressure expansion. I love problems like this. Love is not a strong enough word. Is there a stronger word than love? We've talked about love on Wednesday in this class too. I'm madly in love with problems like this. I have a passion that cannot be denied for problems like this. Because as a thermodynamic professor, this gets me going because it gives me a one problem has 3 problems inside of it. And that's the best way to give you a problem because you want your money's worth when you come to an exam. You're like, I don't want to have 25 points where I just have to plug and chug. I want 25 solid points. And you can get it out of here because there's 3 problems inside of here, 3 different work modes that we have to look at. Okay? Right now, everybody here should be able to tell me if my question here, the question here is, what is the total work? Or I can say, what is the summation of the work? Or I can say, what is the net work? Or I can say, what is the work of this cycle? It's a cycle because it starts and ends at the same point. If that's my question, I have to look at every individual process and find out what the work is for that process and then find out what the total is. So the first thing I'm going to do is I'm going to draw a picture. Okay? PV, and this isn't going to be, I want to keep it on the screen here. So I have 2 pressures that I'm going to deal with, and that is going to be 50 psi, and this is going to be 10 psi. And I have 2 volumes, but I only know one of them. Okay? How do I find my missing volume? How do I find V2? What do you mean a basic ratio?
So if you were to multiply the 2 numbers together, or multiply P1 and V1 together and then divide by...
Yeah, you're saying the right thing. I would say it a little differently, but you're saying the right thing. I can use this. These pressures are connected by this equation. PV is equal to constant. So I know that P1V1 is equal to the same constant as P2V2 is equal to, so I can set those 2 things equal to each other. And so here I'm going to have my pressure 1 is 10 psi, and my volume 1 is 4 feet cubed, and my pressure 2 is 50 psi, and my volume 2 is unknown. And just looking at that mathematically, I know that volume 2 has got to be less than volume 1 because it's going to have to get this ratio working out here. So I type it into my calculator, 10 times 4 divided by 50, and I get my volume 2 is equal to 0.8 feet cubed, and that makes sense. It also told me it was compression, so I should think that the volume should be smaller. A lot of things hints should be if I'm getting the problem right or wrong. Okay. So now what I want to do is I want to put on my points out here. This is going to be my point 1, and this is going to be my point 2, and this is going to be my point 3. And I'm going to draw a line to connect them, and I'm going to be dang sure that I draw a curved line between 1 and 2. And then I have my straight line here and my straight line here. So what I'm really trying to find in this problem is the area inside of this shape. But I'm going to do it piece by piece. I'm going to have some positive works, I'm going to have some negative works, and I'm going to work with them all. Okay, without doing a calculation, each of us should be able to look at this and say, I can give you the work for one of these processes right now without putting my pencil to the paper. And which process is that you can do that for? The constant volume process. Constant volume process has no boundary work. Okay, so we can already say here, easily, we can say that work 2 to 3 is equal to 0. And And we're in here, so this is going to be BTUs. And now we can just pick which one, next one we want to work with. I'm going to go ahead and work with the constant pressure work because I think that's the second easiest one to deal with. And so I'm going to say work 3 to 1 is going to be equal to the integral of P dV. And remember, this is going to be work from 3 to 1. And so this is going to give me pressure is constant, so pressure comes out here, and I'm going to have V1 minus V3. Now, this is another thing that a lot of people always think when they're doing these problems. It's got to be the big number minus a small number, and that's not right. It's got to be the final state minus the initial state. Final state happens to be called the number 1, and the initial state happens to be called the number 3. Okay, don't get caught up in it. It always has to be a bigger number minus a smaller number. This happens all the time and messes up. It usually gives you the right magnitude but the wrong sign. So make sure you're okay with that. Okay, so what do we have here? This one, the pressure was 10 psi. I'm going to put pounds force per inch squared. My volume 1 is 4. My volume 3 is 0.8, and this is going to be feet cubed. We now have to do, that's the equation. We have to now make sure we have our units taken care of here, and so we first have to take care of our inches. We know that 144 inches squared is in 1 square foot. And so what does that do? Inches goes away, and 2 of our feet go away, so now with pounds force feet, and we know that 778 pounds force feet is in 1 BTU. So again, these conversions are big, and I told the 830 class, I think there's probably about 10 points just of worth of just if you make sure your units are right, that's on every exam. So please make sure your units are right. So if we do this, 10 times 4 minus 0.8 divided by 778 times 144, this gives me 5.92 BTUs. And it's positive. And it should be positive because I know on my diagram it is going from, it's expanding, going from 0.8 feet cubed to 4 feet cubed. So I should be comfortable. Okay, I'm not sure if I type things into my calculator right, but I do know that it's positive and it should be positive, so that gives me a little bit of comfort. If I got a negative number, I would have to think, oh, I may have did something wrong and I want to go back and check it. Okay, let's go now and do the missing one, work 1 to 3. It was PV is equal to constant, so I know right there this is a polytropic process with N is equal to 1. And so I can choose P1 V1 natural log of V2 all over V1 to solve it, or I could do P2 V2 natural log of V2 over V1. It doesn't really matter which one I use. 1 to 2, thank you. It's 1 to 2. This is what I miss about home when I'm lecturing at home. I can make a mistake and I'm talking to the computer and the computer doesn't talk back to me. You would talk back to me, and my kids, they don't care about this at all. I've tried and tried and tried, and my wife, she really doesn't care about this. So I'll get an email and later on say, Dr. Wanklin, for the whole class period you were talking about this, and I think you were wrong, and I feel bad, and I have to send out this retraction. So yeah, I'm glad you're here to catch me on that. Okay, so what is this? P1 V1. Well, that was going to be, if we go up here again, I'll keep it down here so we don't, I'll go to my notes here. P1 is 10 psi. V1 is equal to 4 feet cubed. Natural log V2 is equal to 0.8 feet cubed, and V1 is equal to 4 feet cubed. Feet cubes cancel, so I don't have to worry about them there. The units cancel. Okay, and so I have to remember here again, I'm going to have those same unit issues. So I'm going to say 144 inches squared for 1 foot squared, and I have to do 1 BTU is equal to 778 pounds force feet. So now I'm going to type this into my trusty calculator. 10 times 4 times the natural log of 0.8 divided by 4 times 144 divided by 778. This is giving me this work here is negative 11.92 BTUs. And that it's right, it's compression. It should be. And if I look at my diagram, it should be actually larger than my work 1 to work 3 to 1. There's more area under that curve. So now when I want to find out what the summation of all the work is, that's going to be 0 plus 5.92 minus 11.92, and that's going to give me minus 6 BTUs. So for this process, this series of processes, I should say, this cycle, it's going to net require 6 BTUs of energy from the surroundings to the system. So if I had to put this in words, net, the surroundings is going to provide 6 BTUs to that system. Are there any questions about this example problem? Again, if you don't see a cycle problem on the first exam, something has seriously happened to me. Call, find out what's wrong, okay? Because I have really messed up. I like cycle problems on those first exams. All right. We'll do one more problem and then I'll let you go. So this problem, example 2, we have air again in a piston cylinder, and they tell us that P1 is equal to 1.4 bars, and V1 is equal to 4.25 meters cubed. And they tell me that P2 is equal to 7 bars, and they tell me that the relationship is PV to the N is equal to constant. They tell me it's polytropic with PV to the N is equal to constant. And they tell me that N is equal to 1.3. They give me the polytropic exponent is 1.3. They want me to find out what the work is. Okay, so this is just, I'm doing this problem just because it's in SI units, because it has another thing that students often struggle with on exams. Okay, so how would we do this problem? Well, to do this problem, we have to find out what V2 is. We have to, because we know it's polytropic with this. We know work is equal to P2 V2 minus P1 V1 all over 1 minus N. We know that, and we look here and we say, oh, I know P2, I know P1 V1, I know N. The only thing I don't know is V2, so I have to find V2. Okay? And so I am going to say that P1 V1 to the N is equal to P2 V2 to the N. And now I'll start plugging things in here. 1.4 bar times 4.25 to the 4.25 meters cubed to the 1.3 is equal to 7 bars times our unknown volume to the 1.3. Don't have to worry about units here because the units in volume will be meters cubed. And so I'm going to solve this. I'm going to take 1.4 and take it times 4.25 and raise that to the 1.3 power and divide that by 7. And I'm going to get 1.312 is equal to V2 to the 1.3. And this is where I get a number of students that either panic or don't know how to use a calculator. Okay, because there's many ways to solve this. Many, many ways to solve this. I like to use the x root. I like to take the 1.3 root of 1.312. That's actually fun how that worked out, right? But know how to use it. Know how to do this. Okay, it shouldn't be too difficult for you. So I do this, 1.312, and I get that my volume 2 is equal to 1.232 meters cubed. So again, I started with 4.25 meters cubed. I'm down to 1.232 meters cubed. I should get a negative answer because I should have that I'm compressing that air and working with it. Okay, so now it's simply put it back into this top equation. The work is equal to P2V2, which is going to be 7 bars times 1.232 meters squared, minus P1V1, which is 1.4 bars times 4.25 meters squared, divided by 1 minus 1.3. Okay, so if I put this into my calculator, 7 times 1.232 minus 1.4 times 4.25 divided by 1 minus 1.3, I get an answer here that is negative 8.913. But I'm not done. Because even though I get my answer correct in this class, I want to teach you, can we check the units? And the units here are bars, meter squared, and that's not our unit of work. Our unit of work is a kilojoule. So we have to take care of this. So the first thing I want to do is get rid of those bars, and I'm going to say that 1 bar is 10 squared kilopascals. 100 kilopascals is 1 bar. Okay? Well, that's good. Now I have kilopascals meter squared. So as we're getting used to this, let's say that 1 kilopascal is equal to 1 kilonewton per meter squared. And so what we're going to have here is kilopascals cancel. I messed something up, didn't I? You didn't yell at me. You didn't yell at me. This should be meters cubed. Meters cubed. My units, all of a sudden, I was getting messed up here. This should be meters cubed. There we go. We fixed it. We get this. We have kilonewton times a meter, which is a kilojoule, which is exactly what I want. So I basically take this number times 100, and my answer is 891.3 kilojoules. That's my final answer. So again, if I wanted to put this in sentence form, I would say the surroundings, or this process requires 891.3 kilojoules to complete. I want to emphasize, you saw I made a mistake. And I'm not one of those professors that's going to say, oh, I made the mistake because I wanted you to pay attention. No. I made the mistake because I'm a dumbass. Okay. I am just like you. I mess up things all the time. I find myself, if I catch myself, if I follow the units, I usually can catch myself and say, oh, that's where I made the mistake. And there are other times when I look at this answer and I'm going to think, man, that Wiley plus must be wrong because I've tried this 1,000 times. I'm sure I'm right. And then I realize I made some simple error. Those things happen. Those simple errors happen. I am not going to count you off on simple errors. I'm going to have to count you off on simple errors on the exam, 1 or 2 points. But the big conceptual ideas, if you can get the main equations in there, you're going to get 23 out of 25 points. Maybe nickel and dime, you mess something up here and there. So make sure you understand the process. And if we can get these skills of unit watching and work and everything like that, if we can get that solidified, then when we bring in these more tough issues and ideas, you're going to feel more comfortable with this class. And then all this preparation I've said about, hey, it's going to get more difficult. You're like, what do you mean more difficult? This is not so bad. Yeah, because you're not trying to learn and get all this stuff solidified. You have a really good, solid foundation. All right. Any questions for me? All righty. That's what I have for you today. On Monday, we will talk about the first law of thermodynamics completely, and we'll work some problems there. And we have about 1 more week in Chapter 2 before we get to Chapter 3. If you do not have your appendices printed out and ready to go, you should be working on that and getting that taken care of so that you have it in your possession. And we will see you next week. Have a good weekend. Stay out of trouble.